Okay, so we are done with the whole numbers addition and subtractions, right? We are moving on to multiplication today. So there are several models for multiplication as well. The first one is repeated addition models. So multiplication is repeated addition, then similarly division later when we're talking about that, we're going to talk about repeated subtraction, right? So we are repeating the same number addition and we can develop that as multiplication, right? For example, 8 plus 8 plus 8. I am adding 8 repeatedly 3 times. So instead of just adding 8 3 times, I can say that it's 3 times 8, right? Or you can say that 8 multiplied by 3, right? 8 multiplied by 3 or 3 times 8. And what do we call these numbers 3 and 8? We call them factors. And the answer 24 is the product. If you guys remember, in addition and subtraction, I also taught you about the numbers of the components, right? For example, 2 plus 3 in addition is 5. These two are called addends. These two are called addends because the order doesn't matter. This is addend, that's addend. Both are added, right? And the answer here, what do we call that? Yes, very good. Sum. How about in subtraction? What if we are doing 5 minus 1 is equal to 4? Are these two numbers have the same names as like addends? No, right? Because you cannot use a commutative property. 5, the number that is subtracted is called subtrahend. And the number that is subtracting is called minuend. It's minusing that number, so minuend. What's the answer? That is called, yes, the difference of two numbers. Okay, in multiplication, if we are doing 2 times, let's say 5, that is 10. 2 times 5 is 10 and 5 times 2 is also 10. So we can use the commutative property here in multiplication as well, right? So both are called factors. Then what do we call the answer of multiplication? We call that, yes, product. Sorry for that handwriting. We will talk about this for the next section, but in division, if we are doing 8 divided by 4 is equal to 2. That's different from 8 divided by 2, right? So, and 4 divided by 8. So we cannot switch them around, right? So what do we call the number that is divided? That's called a dividend. How about the number that is divising? That's a divisor. It's divising the number, divisor. What is the number in the answer? We call that quotient. Well, sometimes it has exactly quotient, but when there is something remaining, we call that as remainder. Okay, so that's brief review about the terminologies. Okay, so we call that factors. You can use the number lines to show this repeated addition, right? So we can do 8 plus 8 plus 8 with a physical apple, 8 red apples, 8 red apples, and 8 red apples all together. There are 24 apples. You can do that, and you can also do the number lines. So, for example, if we are doing 4 plus 4 plus 4 plus 4 plus 4, that shows 5 times 4, right? 4 is added 5 times. 1, 2, 3, 4, 5. Right? So that is 5 times 4, and you land on 20. So 20 is the product, 4 and 5 both are the factors. We can also use the equal groups model. So it's similar to the repeated addition. Just like that, we have each group with the same number elements in it. So let's suppose, we can see that in each circle, I have 4 x's there. So how many x's are there in total? I can do 4 plus 4 plus 4, but I can also say that, there are 3 groups, and in each group I have 4 x's there. So the total x's is 12 x's. So here you can name these differently. The units are different, right? So I have 3 groups of 4 x's, and the answer is groups or x's. Yes, 12 x's. Okay, all right, something like that. So multiplication is about coordinating numbers and sizes of equal groups. We know that. So number of groups, how many groups? 3 groups of number of objects, 4 objects. And total objects are there, right? Okay. So remember, in this picture, I have cookies. I have 3 3 plates of cookies, and in each plate I have 5 cookies. So I can say, what's the group? How many groups? How many plates? 3 plates of 5 cookies. How many cookies are in total? 15 cookies are in total, right? Okay. Array model. We do this a lot of times too, because it helps us to understand it better, because we know how to find the rectangular area. So array and area model goes together. At rectangular array, you can see that how many rows or how many columns, right? So in this example, I'm showing the rows. How many rows are there? Just like groups, I have 1, 2, 3 groups or 3 rows, and in each row I have 4 x's. So I have 3 rows of 4 x's. The total x's is 12, right? Okay, here's another example with a real world situation. How many cans viewed from above are shown below? Okay, so if you have a bird's eye view on the cans, it looks like this. It's array model. So you can either count by the columns or you can count them by rows, right? If you're counting these by the columns, you can say 1, 2, 3, 4, 5, 6 columns, and in each column I have 4 cans. So 6 columns of 4 cans. 6 times 4, 24. Or you can look at these as rows. You can say 4 rows, and in each row I have 6 cans. So 4 times 6 is equal to 24 cans. Right? You can also use this. Rack and rack. I love rack and rack. So for example, if we are doing 6 times 4, I have 6 plus 6 plus 6. You can see that makes 10, 20, and 4. 24. Students can find the answer very easily, right? Even for the bigger numbers like 10 and 6 times, let's say 3. So I'm gonna have 10 and 6 3 times. Another 10 and 6. So we can easily see that 1, 2, 3, 4, 5, 6. 5 tens. 5 fives. That is 25. But I also have 1, 2, 3. Oops, I didn't make this is 10. So well, here I can see that this is 10, 20, 30, and I have only red. 35, 40, 45, and the ones. 46, 47, 48. So that makes 48. So easily you can find 16 times 3, right? Using rack and rack. So you can use that in your classroom too. Okay, so this is array model. Okay, you can either, oh, sorry about that. You can either count them as rows, number of rows, and or number of columns. Okay, area model. I love area model. So I want you to know how to use the area model too. It's just like array model, but we are not counting how many objects are in it, but we are using the area of a rectangle. Okay, so for example, if we are doing 4 times 3 or 3 times 4, you can make a rectangle and see how many squares are in that. So to represent 3, you can show 1, 2, 3. To show 4, you can do 4, 2, 3, 4 here. 3 times 4 is how many squares in this rectangle are, right? So 3 times 4 is 12. We can always extend this for longer digits of the numbers. And this area model is very related to Common Core State Standards of Mathematical Practice. The 7th one, look for and make use of structures. Okay, so take a look at this example. I love this free math app too. This is something that I wanted to introduce you to. So this one has a lot of good stuff like fractions, GeoBoard, math clock, number frames. Yeah, you might have already read that article for number frame, 10 frame, number lines there. So a lot of good things, number rack, number pieces, etc. And I will use this one. Not that. Hold on. Oh, partial product here. This one is what I wanted to show you. Open app here. Okay. So we know something like 5 times 4. We know 5 times 4. And we can count how many there are. How many squares are in this rectangle? 5 times 4, 20 of them, right? You can always extend this to bigger digits, like 24 times 25. 25 is too easy because we are so used to with a quarter. How about 24 times 7? Let's make it. So we have 24 times 7, but what I'm going to do here is I'm going to make this into 20 and 4. So because 20 is easier to multiply by 7 rather than 24 times 7, right? So the reason why I'm decomposing 24 and 7 is just to make it easier. So we know that it's still the same rectangle, right? Nothing has changed. I just find partial product here and there and add them together. So this rectangle, area of this rectangle is 20 times 7, which is 140. And this rectangle here is 4 times 7, 4 times 7, which is 28. So together it is 24 times 7. But it's so much easier to calculate 20 times 7 and add that by 4 times 7 than just do 24 times 7. Because we know that this is 140 plus 28, which is 168, right? So it comes to you so much easier. Okay, so that is the area model. Okay, here's another area model that I'm showing with 2 digits. So 73 plus 64. I can decompose by each digit. So 70 plus 3 and 60 plus 4. You can switch these around. It doesn't matter. Still same big rectangle. The partial sums changes. The order of partial sums changes, but it is still in this. Okay? No matter how you decompose, it's still in this big rectangle, and the area of this big rectangle doesn't change. Okay? So you can decompose as you wish. So for this case, I'm gonna just break tens and ones, 70 and 3. 70 times 4 is 280. 3 times 4 is 12. 70 times 6 is 4,200. 60 times 3 is 180. So you add them all together. Then you get this product. Okay? When you are using the standard algorithm, you can take a look at that. 3 times 4 is 12. The partial product is not given here, but we can take a look at this and compare that with these numbers. 3 times 4, 12. Right here. 70 times 4. 70 times 4, 280. Right here, 70 times 4. 3 times 60. 3 times 60. Right here, 180. 70 times 60. 4,200 right here. 60 times 70 right here. So all of these four numbers are added here together. Okay, so I think area model is so much easier. Okay, Cartesian product model. This is ordered pair. So it's more like counting problem that you wanna work in Math 238 right before you do the probability. So for example, like you are picking the outfits when you have like 3 t-shirts, 4 pants, usually the other way around, 4 shirts and 2 pants, 4 pants, 3 pants, whatever. And you're gonna find how many different outfits I can make using these 4 shirts and 3 pants, right? So things like that. So for this example, a restaurant serves cheese sandwiches that are made from a piece of bread and a piece of cheese. There are 3 types of bread to choose from: wheat, white, and rye. And there are 4 types of cheese to choose from: cheddar, provolone, Swiss, and American. How many types of cheese sandwiches can the restaurant make with these choices? What is the best way, the systematic way to find number of combinations here? Well, I will start with bread. So I can have white bread only, white, 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 white. For each white bread, I can assign different cheese: cheddar, provolone, Swiss, American. For other types of bread, I will do the same thing. So wheat bread, cheddar, provolone, Swiss, American. For rye bread, you can have cheddar, provolone, Swiss, and American. So we didn't miss anything. We counted all of that, which is exactly same as 3 times 4, isn't it? 3 types and 4 types, 3 times 4. That's how you can count, right? Because take a look. If you are using this tree diagram, it's called a tree diagram because it has trunks and branches here, right? So we're gonna make sandwiches with 3 different types of bread. You can start from cheese too. You can start from 4 different cheese, and each 4 cheese can have 3 breads. It's the same thing. So if you are starting from 3 different breads, each bread can have 4 different types of cheese, right? So we have ordered the pair here, organizing list, and you can see that there are 3 groups: 1 group, 2 group, 3 groups. For each 3 groups of bread, you can have 4 different sandwiches there using the 4 different cheeses. So you can use tree diagram or organize the list in equal groups. Okay, let's talk about the properties. I know, I'm sorry for the overwhelming knowledge here that I'm pouring into, but it is very related to the previous ones that we talked about in addition and subtraction. So you can just extend your knowledge, okay? It's not something new that is not connected to the previous lessons. Okay, properties of multiplication of whole numbers. Think about closure property. What is a closure property in addition? The add-ins are the whole numbers. When you add them together, you have a unique whole number, right? Similar to that, in multiplication, For any two whole numbers, a and b, if you multiply them together, you get a whole number product. 2 times 3 or 3 times 2 or 1 times 4 is always a new whole number, right? Okay, it doesn't have to be different from the previous one. Like 4 times 1 can be 4, but it's unique. Why do we call that unique? Because 4 times 1 has only one number. There's no other number for that product. Okay, that's why we call that unique. Because of the closure, we can think about other properties. Let's think back our subtraction. Subtraction in whole number, the closure property didn't work, so you didn't even have to think about other things. Community property, associative property, identity property. No, you don't have to think about anything, right? But just like addition in whole number, closure property works for multiplication. So we need to consider commutative property, associative property, identity property. Okay? Commutative property, you can commute the numbers around. So 2 times 3 is equal to 3 times 2. Associative property, you're associating these two without changing the order. It's same as associating the other two. Identity property, you multiply a number, you get the same number. So when you are multiplying by 1, you get the same number. And there's one more property, actually two more, but another one is multiplication property of 0. Oh, it's powerful. Because whenever you multiply by 0, that number becomes 0. Is this so powerful? Okay, so here are some examples. In multiplication, we know the closure. So any whole number, this is 2 is an element of a whole number, 4 is an element of a whole number. So 2 times 4 is also a whole number. Okay? Commutative property. So 2 times 4 is the same as 4 times 2. You can switch the order around, right? You can commute them around. They're still the same. Associative property. If you have more than 2 numbers, well, even if I don't put the parentheses, you need to do that from left to right. So 2 times 3, which is 6, 6 times 4, 24. You're gonna do it this way, right? That's same as 2 times, you associate 3 and 4 first. So 3 times 4 is 12, 12 times 2, 2 times 12 is 24. So that is associative property, right? Identity property, you give yourself identity. So 2 times 1 is 2, right? In addition, 0 makes the identity property, but in multiplication, you need to have times 1. That's same as 1 times 2, like 100 times 1 is 100. 1 times 100 is 100. Things like that. You multiply by 1 and you get yourself. That's identity property. And 0 property. Whatever number you have times 0 makes 0, right? That's 0 property. Lastly, distributive property of multiplication over addition or subtraction. So you have something like 3 times 2 plus 5. You can distribute 3 to each of that end. Then you have 3 times 2 plus 3 times 5. So 3 times 2 plus 3 times 5. 6 plus 15. Which is 21. That's same as 3 times 2 plus 5, 7, 21, right? Okay, so that is the distributive property. Okay, so commutative property of multiplication. Well, you can see that the rectangle area of rectangle doesn't change even if you do the 3 times 5 or 5 times 3. Okay, associative property. well, you have at least 3 numbers. So if you have 2 numbers, it's 2-dimensional. If you have 3 numbers, it becomes 3-dimensional. So like volumes, right? We have 1 row, 2 rows, 3 rows of the flats. Each flat have 5 times 4 of area. So 5 times 4, and you multiply that by 3. So 3 times 5 times 4 is the same as, it's the same rectangular prism. If you put them together, that's same as 3 times 3 times 5 flat. How many of them? 4 of them. That's exactly the same thing. Okay, that's what this visual representation shows. And I just talked about distributive property. So if we use the area model here, 5 times 3 plus 4 is this. 5 times 3 plus 4. You see that? 5 times 3 plus 4. That's same as 5 times 7, isn't it? So I can distribute 5 to each of 3 and 4. So I can break this into these 2 parts and have 5 times 3 and 5 times 4. So together, it's the same as 5 times 3 plus 4, right? That's distributive property of multiplication over addition. Oh, we have one more distributive property of multiplication over subtraction. It's the same thing as addition. You are distributing A to B and C, and it's addition. And similarly, you can do A times B minus A times C. That's distributive property. If you go back the other way around, it's still distributive property. So if you have to go back, either case, you need to see what is the common factor. So AB plus AC, both has A as factor, so we call that common factor. Then factor that out. What is left then? B plus C. Okay? Either way, going this way or the other way around, both are distributive property. Same for the subtraction. If you're thinking about going backwards, A here and A is here, so both are, A is in both of the terms. So we can say that A is a common factor, so factor A out, and in the parentheses, what is left? B minus C. Okay? So you can go this way and that way. Either way, you can say, oh, they are distributive property. Okay. 25 times 15. Can you use an area model to find 25 times 15? And can you use distributive property to find the same number? Yes. This is area model, right? So 25 times 15 or 15 times 25, same thing. And you can see that 20 times 10 is 200, 20 times 5 is 100, 5 times 10, 10 is 50, 5 times 5 is 25. And you can see the partial product there. 200 plus 100 plus 50 plus 25. Different order, but same thing. It's 375. So if you're using the distributive property, you can see the similar way too. So 25 can be decomposed as 20 and 5, 15 as 10 and 5, just like this area model, right? But here we can use the distributive property. So you're going to distribute 10 to each of these numbers and 5 to each of these two numbers. So 20 plus 5 times 10 plus 25 times 20 plus 5 times 5. So you're distributing 10 and 5 for each of these numbers. So you get, oops, so you get what? Can I write it here? I don't think so. So you get 400, 20 times 10, 200, this is what we have. 5 times 10, 50, 20 times 5, 100, plus 5 times 5, 25. So you get exactly the same product. Okay, exponents is something new, right? We never have heard of exponents in addition or subtraction. But in multiplication, exponents is a new concept, a very important concept. So when you are multiplying the same number again and again, you can use the exponent. So if we are multiplying, for example, a n many times, so we say n factors, then we say it's a to the nth power. That n is called exponent, and a is called a base. Okay? There are a lot of theorems for exponents. So we will start from this multiplication. Okay, and I will actually do both of them at the same time. Okay, so hey, if it's too long, I mean this video is very long because it's not only for one day, but it is for, how many days is it for? 3.4. Let me look at the syllabus. 3.4. This is for 2 days, September, 2 days. So you can, take a break after like 50 minutes, then you can watch the rest of the video later. Okay, anyways, if you're multiplying, let's do with a real number. How about 3 to the second power? So 3 squared times the same base, 3 cubed. What does this mean? This 3 squared mean 3 times 3. 3 is multiplied twice, right? And 3 cubed is 3 times 3 times 3, right? So we can see that in multiplication, it doesn't matter how you associate, right? So we can do 3 times 3 times 3 times 3 times 3. And we can find that this is 3 times 3 times all of that. How many factors? 5. So 3 to the 5th power, right? And compare this with this. That's exactly same as 3 to the 2 plus 3 power, isn't it? So if you are thinking about this 3 squared and 3 cubed in multiplication, because you have the same number, you are counting how many there are. So you are having 2 3's and you are having 3 3's, and all together there are 5 3's. That's why you are adding them, because you are counting how many there are. Okay, so a to the nth power times a to the nth power is the same as a to the same base. For multiplication, you can just add them together. Okay, if you are having power over power, like a to the nth power, let's look at this example. Let's think about 2 to the 5th power to the 3rd power. What does 2 to the 5th power? Well, let's look at the big picture. Before you do 2 to the 5th power, this to the 3rd power means you're multiplying that 3 times, right? So 2 to the 5th, 2 to the 5th, and 2 to the 5th. So you have 3 groups of 2 to the 5th power. Doesn't that sound familiar? Number of groups of same number. It is multiplication, isn't it? Yeah. So that's why we are using this as multiplication, m times n. Because we have 2 to the 5th, which is 2 times 2 times 2 times 2 times 2. In each of these parentheses, I have 2 times 2 times 2 times 2 times 2. In each of these, times 2, 2, 2, 2, 2. Right? So all together, I have 5, 10, 15. I have 15. How did I get that? I knew that there are 3 groups of 5 factors. So 3 groups of 5 factors, or 5 times 3. Okay? So power over power, you multiply them. Okay? What's next? Okay, now let's take a look at this theorem. A to the n. Okay. Oops, not this one. So when you have not the same base, but if you have same exponents, we can factor that out and have a times b in it. For example, if you have 3 to the 4th power times 2 to the 4th power, 3 to the 4th is 3 times 3 times 3 times 3. 2 to the 4th is 2 times 2 times 2 times 2. I can use associative property and commutative property. So I can have 3 times 2, 3 times 2, 3 times 2. Hard to learn that. Right? So 3 times 2, 3 times 2, 3 times 2, 3 times 2. So I have 3 times 2. How many groups? 1, 2, 3, 4. So 4 factors. I have 4 as exponent, which is 6 to the 4th power. Right? So when you have same exponents this time, previously we talked about same bases, right? Same bases. But now we are talking about different bases but same exponents. Then you can put the exponents out and multiply those two numbers together. That doesn't work for addition. It works only for multiplication. So for example, if you are having addition like 3 to the 4th and 2 to the addition, 2 to the 4th, what 3 to the 4th is 3 times 3 times 3 times 3, and you're gonna add that by 2 times 2 times 2 times 2. There's nothing in common. There's no common factor, so you cannot use distributive property. You just need to do 3 times 3 times 3 times 3, which is 81. 2 times 2 times 2 times 2, 16. You just need to add them together. Okay, there's nothing you can do. Okay, so don't get confused with it. There are a lot of different properties too, so you need to know b to the, oh, that's supposed to be 1, property of 1, so b to the nth power, 1's power is b. So here, oops, okay, I will give you a weird example. Let's look at 2 to the 1's power, which means there's only 2 there, right? 2 to the, 2 squared is 2 times 2. Look at the pattern here. 2 cubed is 2 times 2 times 2. So we know all that, right? 2 to the 4th power is 2 times 2 times 2. 2 times 2. So you keep multiplying 2 more to the previous one. Then guess what 2 to the 0 power is? What could that be? To go backwards, you can just divide each one by 2, right? So divided by 2 is what? 1. 2 to the 0 power is 1. Whatever to the 0 power is always 1. So remember that. Whatever to the 0 power is always 1. Whatever to the 1's power is always itself. Okay? So remember that. And let's go back. Negative power. So negative power, we didn't talk about that, but it's really useful if you get to know that. We will talk about this when we're doing the rational number, fraction number. But briefly, I will just show you. So something like negative 1's power. The negative shows reciprocal. Okay, and that power stays the same. So negative power is reciprocal. That's what you need to remember. For example, a to the negative 2 power is 1 over. The negative means 1 over, reciprocal, a to the 2nd power. Okay? Another example, 3 to negative 4th power. That means 1 over 3 to the 4th. This is not negative number. It's still positive number. A very small number. Okay? Very small positive number, not negative number. Okay, so we talked about same base multiplication. You can add them together, power over power, multiply them, and you can distribute, the exponent. We will talk about this in the rational number again too. So, well, we just talked about this one as well. Remember that, and quotient property, it's okay. We'll talk about that in the rational number. Don't worry. Multiplication algorithm. Okay, so when we are using the base 10 blocks, we can also show the multiplication. For example, if we are doing 12 times 4 or 4 times 12, so we have 4 groups of 12. In each group, we have 12. It's 4 times 12. And you can see that it's 48. It's nice because there's no regrouping. What if you have to regroup? You can see that 12 times 4 or 4 times 12, 10 and 2, 10 and 2, 10 and 2, right? So we can do 4 times 10 and 4 times 2, right? So you can add them together. So we call this as a concrete model using real object. And you can do expanded algorithm. So 10 times 4 is 40, 2 times 4 is 4. So all of this partial product is given and you're going to add them together. That's expanded algorithm. Standard algorithm, you can just do 2 times 4, 8. 4 times 1, 10. That's 4, 10. So 48, right? What if we have any regrouping? So let's give some example. How about some big number? 382 times 6. Using the standard algorithm, we still work from ones place, right? And then tens and moving to the left. So 2 times 6 is 12. There are a lot of different way of writing. I would like to put that 10 right here in the tens place, but still as the partial product here. Okay. Some people put it here, but I think it's kind of confusing to me, so I prefer it here. 2 times 6 is 12. 6 times 8, this 8 is 8 tens, so 48 tens. So 48 tens, but you have another 1 tens, it becomes 9 tens. And 6 times 300 is 1800. So you can have 1800, but because you have 4, 18 plus 4 is 2200. So that's my product for 380 times 6, 2292. If we have some other number, something like 2 times, how about 46? If we are extending it, we can do the same thing, either using partial product or standard algorithm here. If you are using partial product, you're going to do each of them, just like area model. 2 times 6, 12, 6 times 80, 480, all of that, okay? But I'm going to use standard algorithm here. 2 times 6 is, well, we already did that, so I will just copy that, the same procedure that we did here. And for this, it's 40. That's why a lot of teachers don't write anything here, but that means we start from tens, because it's 4 tens times 40 times 382, so there's nothing in the ones. So I prefer to write it 0, and I strongly encourage you to do that too, because students can get confused, and sometimes they push it to the right, so they make mistakes. 2 times 40 is 80. Nothing carries over. 4 times 8, 32. That's hundreds, because tens times tens becomes hundreds, right? And 300 times 40 is thousands, but how many thousands? 12 thousands. But you already have 3,000 there, so 12 plus 3, 5. And you can add them together, right? So you have 2 plus 0, 2, 9 plus 7, 17. Now it goes up here. And you have 1, 2, 2 hundreds, which is 5 hundreds. 2 plus 5 thousands, you have 7,000, and 10,000. So you have 17,572. Okay, you can always extend the same, procedure. Okay, one more thing is lattice model that I want to show you. 37 plus 56. 37 plus times 56. I think everyday math uses lattice model, and a lot of students in eastern side of this country uses lattice model, and I think that's very useful but not very conceptually, more like procedurally. So what you are doing here is you're gonna make lattice like 37 times 56. You're gonna break this box and you're gonna make diagonals here. Okay, and what you're gonna do here is, I'm not writing 56 here. I think it's easier to write 56 here. So 37 times 56. Each square here is the intersection of those two numbers. So for example, this square is intersection of what? 7 and 5. So you multiply these numbers, 7 times 5. 10's digit go up here, 1's digit go down here. So 7 times 5 is 35. And this square here is intersection of 3 and 5. 3 times 5 is 15. Right? And this square is intersection of 7 and 6, 42. This one here is 3 and 6, so 3 times 6, 18. Now, what we are doing here is we're just gonna add these numbers together. So 2 in this diagonal, 5, 4, 8, 9, and 8, so 17, and that 1, 10 carried over here, so add one more up here. 3, 5, 1, 1, 7 and 3, that's 10, so carried over here, so we have another 1 that makes 2, which is 20,726. 37 times 56 is 20,726. That's the lattice model. Did something wrong? Why did I put 6 there? This was 56 here. I'm sorry. Okay, so the answer is here. Only the numbers that we added here at the end. 2072, right? Which is 2000. I think I'm getting tired here. 2072. Okay, so 2072. Let's have one more example with more numbers. Do I have any example, or should I just make it up? Let's see. Here's another one. 948. 827. 948 times 827. 827. So we're gonna have 3 by 3 columns, right? So you can have 948 times 827. 827. And then you can draw the diagonals, because the answers will go to the diagonals. So each corner, I'm gonna connect them. There we go. And then you can answer, fill that up. 9 times 8 goes here, 72. 4 times 8, 32. 8 times 8, 64. 9 times 2, 18. 4 times 2, 8. There's nothing in the tens, so 0, 8. 8 times 2, 16. 9 times 7, so the order doesn't matter in lattice model, so there's not actually conceptual understanding there. But you can also connect that to the place values, because this is ones, and that's tens, and that's hundreds, and that's thousands, and 10,000s, and 100,000s. Okay, so what is this? 7 times 8, 56. 4 times 7, 28. 9 times 7, 63. So we build that up, and now you can just add all of those diagonals. 6, that's ones place. Here, 14 and 5, 19. So you have one more there. 4, 5, 10, I'm sorry, 10, comparable numbers. 10 and 8, 9, so it's gonna be 19. And one more here, so 2 and 8 makes 10, makes 12, 22, and one more, 23. So 2 is carried over. So 3 and 5, that makes 8, and you have 7 there. So this is a big number, but we got that. It's 783,996. Use a calculator to check. 783,996. Okay, very good. And we're gonna move on to the mental computation and estimation here. So very similar to the addition, we can do mental computation and estimation, right? So little kids, again, they tend to multiply from the bigger digits. Like instead of multiplying 4 by 5, they can think about 60 by 5 first. So 60 times 5 is 300, 4 times 5 is 20. Together you can have 320. That's front end multiplying. Using comparable numbers. So when you're multiplying these numbers, how would you do it? I would go with 2 times 5 as 10 and 20 times 5 as 100. So 10 times 100 is 1,000, right? Times 9, 9,000. I think that's a really good way to think about this problem. So you can use the comparable numbers to make it easier. And also you can always think about the money, because we are so used to using monies. So when you're multiplying 64 times 5, that's 5 cents you can think about, right? So 5 cents is what? Nickel. So what is the 64 nickels? How much does that cost? How much is it? 64 times 5. 64 nickels. Well, you can change 2 nickels into one dime, right? So this is the same as 32 dimes. 64 nickels is the same as 32 dimes, which is 320 cents. So this will be 320. Does it make sense? How about when you're multiplying 64 by 50? 50 is half of a dollar. So you can think about this changing 50 cents into $1, which is 100 cents, and you can just half 64 to 32, right? So it's the same as $32, which is 3,200. And 64 times 25, you can think about that as a quarter. So you have 64 quarters. 64 quarters, which is $32.50. $32.50 is same as what? Half of that is 16, so it's $16, right? So $16 is 1,600 cents. So thinking with money is really easy way. And let's think about the estimation. Front end estimation. 500 times 8 is 4,000. 20 times 8 is 160. And when you're adding them together, it's 4,160. Because of its addition, estimation, I didn't even look at 4 times 8 there because it's close to 520. 524 is very close to 520. So I just had 500 times 8 plus 20 times 8. So you can have 4,160. You can change this to compatible numbers, right? So 524 is very close to 2, very close to 525. Why am I changing this to 25? Because of the quarter, the money. So you can think about, oh, I have $500 and 25 cents. 525 cents, right? So you can do 500 times 8, and it's very close to 25. If you have 25 times 8, 25 times 4 is 100. If we have double of that, it's going to be 200, right? And plus 500 times 8, which is 4,000. So you can add them together to get the number there. Okay, so we are done with the multiplication. Very good job. It's lengthy, so please take a break at some point. I hope you did. And if you don't understand anything, please don't hesitate to contact me. Great job, guys. Hang in there.